We are continuing our videos on chaotification, and here we are going to discuss the developments of a recent paper, General Scheme using periodic and non-periodic functions for the chaotification of discrete-time systems, published in Nonlinear Dynamics, link in the description. Okay, I have discussed a lot about chaotification in previous videos. Okay, I don't want to bother you too much. It's about designing new chaotic maps from previous maps. For this paper, we thought of a very specific architecture. Okay, our goal was basically to define, using an original seed map, a new chaotification technique that utilizes a boundary function of a very specific type. What we had in mind was periodic, quasi-periodic, and non-periodic boundary functions. Okay, so the general architecture looks like that. B is a boundary function. F is, of course, as we saw in previous videos, a seed function scaled by a factor of A plus some parameter B that works basically using doing offset boosting. Okay. What we did as a first result is derive, a Lyapunov exponent expression for this very general architecture of chaotification. Okay. Remember, it's very important, apart from numerical simulations, to also include mathematical results. Okay. The very early papers, let's say 6, 7 years ago, didn't do that, and it's very important to actually have mathematical results. So this is our first important mathematical result, the Lyapunov exponent. But not only that, we actually did something very interesting. We considered three generalizations of this architecture. Okay, as you see right here. For all of these three, we have developed Lyapunov exponent formulas. For the third one, I just don't write it, it's very big. Okay, the first generalization is the inclusion of a linear term. Okay, we have plus b times x. Okay, the second generalization, I hope I'm not blocking the view, is the combination of inside the boundary function a composition of seed functions. So we have f1 of f2 of f3. Okay, we have composition of many different seed functions. Okay, and the third one is a multidimensional version of this chaotification. I hope you can see right here. It has an upper triangular architecture, of course, in combination with different boundary functions. Okay, so for all of these, we have formulas for the Lyapunov exponent. And remember, what we had in mind in this paper was to basically utilize boundary functions that are trigonometric, periodic, quasi-periodic, and non-periodic functions. Okay, so I have a couple of examples. We have a couple of examples in the paper. I'm only going to focus on a couple of them. Here I have a periodic boundary function. Okay, on the left is the phase diagram, on the right is the Lyapunov exponent graph for two different parameters. We have wide regions where chaos appears, but it's somewhat interrupted by periodicity. Okay, I hope you can see it right here. So this is one of the examples we have. Another example, we consider the quasi-periodic boundary function. Okay, the previous was inspired by the logistic map with a modulo. This one has a sinusoidal terms, which of course has these scales like here 10p and 5 square root of 10 times p, which creates quasi-periodicity. The Lyapunov exponent diagram, again has wide regions of chaos, but a lot of interruption in between with non-chaotic regions. And the third example, you can see right here, I'm blocking the view a little bit. It's a non-periodic boundary function, kind of like a chirp signal. It has a square if you see right here carefully. Here we have much better results for a non-periodic boundary function. We have much wider regions of chaotic behavior, although of course we still have some periodic regions appearing. Of course, you can have a lot more examples developed, a lot more maps developed, and again we have many more simulations in the paper, but you can read the whole paper to get all of this. One good thing is that we have a very big design freedom because we have to change both the seed function and the boundary function, which gives me really big combination of functions. Okay, we observe that if we have functions that are more rapidly varying, we tend to have less periodicity appearing. Okay, and we also saw that we have robust chaos that appears in some maps. Of course, still we have periodic regions, but for some smaller, I would say, ranges, we can still manage to achieve robust chaos, which is a very good result. Okay. Now, for the future, what do we want to do? Something that we are really interested in with my colleague is to consider variations of the multidimensional chaotification we had. Okay, we had an upper triangular structure. We want to consider maybe non-upper triangular structures, maybe different boundary functions, maybe boundary functions in different architectures for different states of the map. This would be very interesting to consider and see what results we can get. So I really like this future challenge. Another thing is that we want to consider this type of chaotification with these types of boundary functions to develop maps without fixed points, okay, what we call hidden attractors. I have other videos discussing this. And maybe also use piecewise linear functions to achieve similar results, okay. Of course, each one of these can be an individual paper. So if you are interested in codification, from this work you can develop several new extensions, which is a very good thing, of course, for all codification techniques. Link in the description. If you have any questions, just write them down in the comments. And thank you very much.